Good morning, students. Today we will discuss the topic open circuited PN junction. This is the first topic, the first unit of subject electronic devices and circuits. I will share the PPT with you. All of you look at the PPT now. Have a glance at the unit one. There is a PN junction diode. First topic is open circuited PN junction. And we are going to discuss forward bias, reverse bias, current components in PN diode, volt ampere characteristics, temperature dependence of VI characteristics, diode resistance, diode capacitance, effect of temperature on VI characteristics, breakdown mechanism, Zener diode as a voltage regulator, and applications of the Zener diode and diode clippers and clampers. These topics we are going to study. First, we shall see the open circuited PN junction. Before we see the open circuited PN junction, we will see what is the material used and how that material is developed, that we shall see. The semiconductor material is used, and the semiconductor material in its pure form is called as intrinsic semiconductor, and the intrinsic semiconductor added with pentavalent and trivalent metallic impurity atoms results in N-type and P-type semiconductor. This N-type and P-type material is used for fabrication of the diode. The material which we are using, the semiconductor, in which category it falls, if you want to know. So you must know this, the energy band diagram of the material. So here, the first diagram which is shown here, it contains the energy band diagram of an insulator. We have a valence band and conduction band. You can see the diagram. The energy gap between valence band and conduction band is very large. Such a material is, we call it as insulators. The second category comes the semiconductor, wherein the energy band gap is very close to 1 electron volt. And in case of a conductor, there is no gap between the conduction band and valence band, and both are overlapped. Such a material we call it as a conductor. We are interested in a semiconductor. So semiconductor behavior, it lies in between conductor and insulator. Our interest is in only semiconductors because the material used for fabricating diode is semiconductor. Here, example for semiconductor is silicon and germanium. Here we have the atomic structure of a silicon and germanium. You can see the outermost orbit of germanium or silicon contains 4 electrons. That is, silicon and germanium, these are tetravalent atoms. That means outermost orbit contains 4 electrons. When silicon and germanium in solid form, the atoms are tightly bound, and when they come closer, the atom to be stable, outermost orbit of an atom should have 8 electrons. But it is one atom is having only 4 electrons. So what it will do is it will share remaining 4 electrons with neighboring atoms and forms a bond, and that bond we call it as the name of the bond is a covalent bond. That is a bond formed with sharing of electrons. Here you can see the energy band of the same semiconductor material. As the energy gap between valence band and conduction band is very small, if you supply a small amount of energy, extra energy in the form of a heat, the electrons from valence band they will acquire the energy supplied and they will jump into the conduction band. And the semiconductor starts behaving as a conductor because electrons are the charge carriers. And when the electron jumps from valence band to conduction band, there the valence band holes are created. Holes are also charge carriers. Physically, hole is the absence of electron, and when the covalent bond is broken, the electron which is coming out of the covalent bond, it results in a free electron and one hole. Hole and electron both are responsible for the current conduction. That is shown in the diagram. If a covalent bond is broken, electron has come out and hole is created and one electron has come out, a free electron, which will result in a current. When the voltage is applied, the electron will start moving from negative terminal of the battery towards the positive terminal through the device. So this diagram shows the movement of electron and hole. Hole movement is opposite to that of electron, and the movement of hole or the flow of current, which is opposed to the electron current, is called as a conventional current. That is shown in the diagram. And here you can see if the electron is moving from left to right, it seems that the hole is moving from left to right. That is, both the hole current and electron current direction will be opposite. Here we see the N-type semiconductor. So you take a pure semiconductor, add a pentavalent metallic impurity. The pentavalent metallic impurity, which has 5 electrons, uh, the out of 5 electrons, 4 electrons will form covalent bond with the neighboring atom, and 1 electron is free. Like that, one pentavalent metallic impurity atom generates 1 free electron. If we add a few pentavalent metallic impurity atoms, it generates those many electrons and the electrons will be available in the conduction band, and thus the conductivity of the semiconductor is improved. Here we have a p-type semiconductor. In pure semiconductor, add a trivalent metallic impurity. Trivalent metallic impurity has 3 outermost orbit electrons, which will form covalent bond. 3 covalent bonds are complete. 1 covalent bond is having deficiency of 1 electron, which is a hole. Thus, adding 1 trivalent metallic impurity results in a 1 hole in a valence band. Like that, if you add plenty of trivalent metallic impurity, that results in plenty of holes in the valence band. And the semiconductor, in the conductivity of the semiconductor is improved by adding a trivalent metallic impurity. We have seen 2 types of impure semiconductors, that is the N-type and P-type. Now let us come to the topic, that is the open circuited PN junction. So here take a pure semiconductor. On the left side of the pure semiconductor, add trivalent metallic impurity, and on the N side, add pentavalent metallic impurity, which results in a P-type and N-type semiconductor. P-type region and N-type region, where they are joined, that junction is called as a PN junction. When you join PN junction, what is going to happen, that we shall see now. When the P and N junctions are joined, the electrons which are majority carriers N-type, they cross over the junction and join few holes which are nearby the junction, and holes from P region, they cross the junction and join the electrons. The electrons are get neutralized, and here nearby junction, as the atom loses 1 hole on the left side, it becomes a negative ion, and the atom which loses an electron on the right hand side of the picture, it becomes a positive ion. You can see here nearby the junction, there is a region is created, and this region is called as depletion region. And this depletion region has no mobile charge carriers, no holes and no electrons. This region, we call it as a depletion region or transition region, and this region will further stop the movement of holes from P region to N region and electrons movement from N region to P region. In the depletion region, we can see only immobile charge carriers are there, and because of that, the further movement of charge carriers from P region to N region and electron movement from N region to P region will not continue. As holes will try to cross the junction, holes are positively charged particles, and the nearby junction you can see the positive ions, they will repel these holes and they will move away from the P junction, from the PN junction, and the electrons which will try to cross the junction, they will find the negative ions, and electrons are negatively charged particle, and these ions are also negative. They will push the electrons away from the junction, and now at equilibrium, no current will flow, but near the junction, a charge density is developed. You can see in the P region, we have a negative charges developed, and on the N region, we can see positive charges developed. So this charge density will create a field which is the direction of the field will be from positive to negative. That is, from the field will be from N region to P region. And this electric field will develop a voltage. That voltage is called as a barrier potential. And this barrier potential value for the for silicon is nearly equal to 0.7 volts, and for germanium this is equal to 0.3 volts at 25 degree Celsius. This barrier potential, it depends on the type of semiconductor, concentration of donor impurity atom, and concentration of etc. impurity atoms, and intrinsic carrier concentration, and finally it depends on the temperature, that is a surrounding temperature. So this barrier potential, it is indicated by a letter V with the suffix J. Students, today we discussed the open circuited PN junction, and when we join a P and N material, where it is the joining point, it is called as a PN junction, and because of joining P and N region, there is a voltage developed across the junction. That voltage is called as a barrier potential. So in the next class, we shall see where this PN junction is used and what are its application, how can we use this one, that we shall see in the next class. Thank you, students.